this series of videos, we're going to introduce concepts in complex analysis. And we'll begin our study with some definitions and some of the algebraic properties of complex numbers.
Hi everyone, I'm trying something a little new here. I've had a lot of students show interest in complex analysis, and so what I'm going to do is I'm going to introduce this idea as nicely as I can, as smoothly as I can. And there is a lot of interest in this because it is a very interesting branch of mathematics, okay? The idea of an imaginary number just really can't help but be intriguing. What exactly do we mean by an imaginary number? So let's start off with a definition, okay? When we talk about complex numbers, usually we're talking about numbers, and we're going to use the letter Z to represent complex numbers, and we're usually referring to them as an ordered pair. Okay, a complex number can be most easily expressed as an ordered pair here. We've got the x and the y, okay? And the way we talk about it here is we'll use REZ, and this will be identifying the real portion of the variable, and that's going to be x. And we'll use IM here of Z, the imaginary part of Z, to be the letter y. So we're breaking up this complex number into two parts, the real part and the imaginary part. Okay. Now, thus far, I haven't done anything yet with it. I haven't really even said anything other than the fact that a complex number, and again, we're going to use the variable z to represent that, has two parts to it, x and y. The first part's the real, the second part's the imaginary. If we wanted to kind of relegate our entire discussion to the real number system, which is what you would have done up through all your education up to high school, okay, the real numbers here, okay, all of the real numbers have the form, okay, x comma 0. If we simply put a 0 in that second coordinate there, that reduces down to the entire real number system. And so that's kind of how this is based on what you already know. And in fact, we still think about y as being a real number, even though it's in the imaginary part of the complex number, if that makes sense. It's a complex number here, okay? Let me go back up here and we'll talk about it this way. This is a complex number because there are two parts to it, okay? There's an x and a y part. That's why it's complex, okay? But the y part and the x part here, they're both real values. It's just that when we put this all together, and you'll see in a few minutes why I talk about it like this way, this is the real part, that's the imaginary part. Now, let's talk about equality. Okay? Whoops. Let's talk about equality here. So let's say we've got two complex numbers. They will be considered equal to each other if, okay, and let's do it this way. Let's be really clear on this. If and only if the x coordinate, the real part of the first number, is equal to the real part of the second number, and the imaginary part of the first number is equal to the imaginary part of the second number. Okay? In other words, both those pieces have to be identical to each other in order for these two complex numbers to be considered equal to each other. So that's how we understand equality. Now, let's take a look at a couple of operations here. So we've got equality there. Let's take a look at something a little bit more interesting. Whoops, sorry. Let's take a look at addition. Okay, so let's say we've got Z1, we're going to add it to Z2. Addition is actually one of the easier things to identify here. It's actually quite simple. That is simply going to be x1 plus x2, comma, y1 plus y2. Okay, the result is simply the sum of the real parts and the sum of the imaginary parts. Okay, let's try something a little different here. Let's try multiplication. Now, this is where we're really going to see things take a little bit of a turn here, and where you're going to understand a little bit deeper now the nature of the complex number. Okay, because multiplication's got a slightly different definition to it. And I'm going to take you through this expressed definition here and show you where the really popular letter I comes from here. But z1 multiplied by z2 is not x1 multiplied by x2 comma y1 multiplied by y2. Okay. Instead, it looks more like this. It's going to be x1 x2. Okay. That's part of it's correct. But here's where we differ a little bit. Minus, okay, y1 y2. That's the real part of the product, comma. The imaginary part is going to be y1 x2 added to x1 y2. Kind of a bizarre way to define multiplication here, but it's going to make sense in a second here why it works that way. Okay? So anyway, let's jump into this and let's talk about where this is going here. Okay, so let's, for example, take a look at multiplication here. Let's take a look what happens when we take the value that's strictly imaginary here. Okay, so let's say we take, let's do it like this. Let's take the point here. Oops. You take the point, let's say 0, 1, and let's square this. And this is where we're really going to get into that part of the imaginary numbers that most people are kind of aware of at this point and are looking for in this context here. So if I square this, okay, and just look at my definition here, this is x1, this is going to be x2 as well. So this is going to be 0 multiplied by 0, okay, minus 1 multiplied by 1. Okay, so this is going to be negative 1, comma, just by our definition here. Now take a look here. y1 multiplied by x2, well, that's going to be 1 multiplied by 0 plus 0 multiplied by 1, so it's going to be 0 here. So this definition of multiplication that we've just listed out here, when I apply that to a number that's basically the unit in the imaginary position, when I square that, I get negative 1 as a real number. Okay, and so what we do here, it's such an interesting result here, that what we're going to do here is we're going to call that, okay, we're going to let I be equal to that number there, 0, 1, which is strictly the imaginary number. Okay, sorry, this is the imaginary part of that number. So when we drop the real, it's just the imaginary part right there. We're going to call that I. So now, by definition here, therefore, I squared is equal to negative 1. Okay, and so that's where that comes from. We've got this really interesting definition for multiplication, and that's what takes us to this idea of the imaginary part of this number when it's being squared giving you negative 1 as a result. Yeah, which is really quite cool. Okay, so now this allows us to adapt our definition a little bit, and then what I'm going to do is I'm going to come back here and I'm going to show you how this works here. So now what we can do is we can take and write any imaginary number now. So therefore, we can let x comma y, because of what we've just done here, what I can do with this is I can rewrite this as a number in this form, x plus I y. Okay, and so now what we've got here is this ordered pair is going to be replaced by this binomial, if you will. I've got the real portion and the imaginary portion. They both still exist here, but what I'm going to do here is I'm going to use I as the coefficient of the imaginary part. That's what is going to create some of these rules that we've got established here. So just to show you that the rules are still the same, or the rules for addition and multiplication still work here, let's let z1 be x1 plus I y1, and z2 be x2 plus I y2. Okay, and now I'm going to add those together. So z1 plus z2. And when I do that, it's like taking these two binomials and adding them together. Okay, so I'm going to get the real part plus the real part. So it's going to be x1 plus x2 plus, and notice when I add these together, I can factor out the I. It'll be y1 plus y2. And so the sum, if I go back up here, the rule for addition is essentially the same. Okay, well, essentially the same. It is the same. Okay, just the notation's a little bit different here. Now, but more interesting. Okay, more interesting is what happens when we do a multiplication. So z1 multiplied by z2, and I really like this. I really like this because if you're at this point here where you're watching this video because you're interested in complex numbers, you very likely have the algebraic tools that you need to understand where this is going here. So we're going to multiply these two binomials together. This x1 plus iy1 multiplied by that by x2 plus iy2. Okay? Now, it's just distribution. x1 multiplied by x2 is x1, x2. x1 multiplied by iy2 is going to be plus I x1, y2. Okay. iy1 multiplied by x2 is going to be plus I x2, y1. And I'll probably change the order of that in a second, just to be consistent with what we have above here. But now watch this. iy1 multiplied by iy2, that is going to get me I squared y1, y2. Whoops. y2. Now, that's really interesting because of the presence of that squared I there. So x1 plus x2, this is also going to be real right here. That I squared is going to be negative y1, y2. And I'm going to add to that those two terms that each have an I in there, and I will factor out the I, and I will get x1, y2 plus x2, y1. I'm just going to leave it the way I had it written here. Now, take a look at what I've got here as a result. Oops, sorry, just let that slide a little bit. Take a look at what I've got here as a result and compare that to this bit of that I've got here for multiplication. It's the exact same thing. Okay, so it's actually a lot more intuitive to think about complex numbers as being the sum of an of a real part and an imaginary part. But the way I identify the imaginary part is simply to multiply, okay, a real value by I, okay, the imaginary number. Okay, so now that you've kind of gotten a bit of an introduction to that, we're going to take a look at some more algebraic properties. Okay, some of the algebraic properties that we want to look at are properties that you are already very familiar with. We're just going to show you how they relate to complex numbers. For example, the commutative law. Okay? Or the commutative laws, I suppose, because we've got addition and multiplication here. So if we've got two different complex numbers here, z1 plus z2, that's the same as z2 plus z1. With addition, order doesn't matter. And I can say the same thing about multiplication. Z1 multiplied by Z2 is going to equal Z2 multiplied by Z1. Now, I will go through and quickly demonstrate this for you because we've already written out the rules for multiplication and addition here. I just want you to notice this. And remember that complex numbers are built using real numbers here. So let's say we've got, this is going to be x1 plus y1i plus x2 plus y2i, okay? Is that the same as x2 plus y2i, whoops, I'm running into this next one, added to x1, 1 plus y1i? Well, the answer is yes, because remember, with real numbers, order doesn't matter, okay? So I can change the order here, so this is going to get me x1 plus x2, okay, there's my real component, plus, and I can factor out the I there, so y1 plus y2, okay, fair enough. Over here, this is going to be x2 plus x1, plus I, factor that out, y2 plus y1. Okay, and notice, because these are real numbers here, order doesn't matter here, so as a result, these are going to be exactly the same as each other. Okay, now let's take a look at how the commutative law applies to multiplication. So z1, z2, okay, when we multiply those together, we've already seen that what we're going to get here is x1, x2 minus y1, y2 plus I, the imaginary number, multiplied by x1, y2 plus y1, x2. Okay, so that's what happens when we multiply those together here. Now, when I multiply z2 by z1, what that's going to do is it's going to change the order of these variables here. So it's going to be x2, x1 minus y2, y1. Now you can follow that through. You can actually go through and apply those rules yourself there and double check that. Now, did that change anything? Does order matter with multiplication? Well, with real numbers, no. So these are exactly the same expressions here. Now, what happens here? The x1 and the x2 are going to change here. So this is going to end up being x2 y1 plus y2 x1. And now take a look what that's done in this, the imaginary part of this complex number here is it's taken those two terms and just swapped them. Now, does order matter with addition with real numbers? And the answer is no. So these are exactly the same. So we've been able to verify that the commutative law works with multiplication as well as addition. Now there's a couple other laws that you need to be aware of and that they hold here. For example, the associative law, okay, or the associative laws we'll say, meaning that if you've got, for example, Z1 plus Z2, add those together, whoops, in parentheses there, if we add Z3 to that, okay, the result that we're going to get is going to be identical to adding Z2 and Z3 first and then adding Z1 afterwards. Okay, just like if we do multiplication, Z1 multiplied by Z2, then multiplied by Z3, will give you the exact same result as multiplying Z1 by Z2 multiplied by Z3. Order doesn't, the way you associate them doesn't matter. Okay, another rule that you guys we're going to need to be familiar with here, and we could prove these. I could go through and prove these, but the proof is going to be very similar to what I did with the commutative laws. You're just going to use the components of the complex number, apply the operations, and because these rules work with the real numbers, they're going to work with the complex numbers. So the other one to look at here is the distributive laws. Okay, and essentially it's the same old here. If you've got Z1 multiplied by Z2 plus Z3, okay, you will get Z1 multiplied by Z2 plus Z1 multiplied by, multiplied by Z3. Okay, that's what you're going to get. Those are your distributive laws. Now, let's move on and take a look at a couple other ideas that really do need to show up here. We need to verify how they work here. First of all, when we talk about addition, okay, when we talk about addition, we need to make sure that there's the additive identity. Okay, so we're going to talk about the additive identity, and in this case here, what that's going to look like is the the complex number 0, 0. Now, when we say additive identity, what I mean by that here, we'll just let this be equal to 0. Okay, right? That's your complex form of 0 there. If I take Z1 and add 0 to it, nothing happens to the identity of that number. It stays Z1. Okay, and that's because whatever we get here, if we've got x plus yi, if we add this to 0 plus 0i, if we add the real components, add the imaginary components, okay, x plus 0 is x, y plus 0 is y, so we still get x plus yi. So there's your additive identity. Okay, now at the same time, this introduces the possibility of additive inverses. Okay, so the additive inverse, okay, is going to be when you have a number here like Z1. If I can add that to some other number here, which would be its inverse, okay, let's say Z2. We'll call Z2 the additive inverse of Z1. The answer's got to be equal to 0. That's true so long as Z2 is equal to the negative of Z1. And by the negative, what I mean is specifically this, and actually it makes more sense to write it out like this. If I've got x1 plus y1i, okay, and I'm going to add to it some number here such that the result is going to be 0. Now, 0 real component, 0 imaginary component. This has got to be negative x, not necessarily plus, probably makes more sense to write like this, minus yi. Okay, so x1 minus x1, y1 minus y1. So they all cancel out here, and you're getting that 0. So there's your additive inverse here. And we can take let's use an example here real quick. Let's say, for example, I had the complex number 2 plus 3i. Okay, if I added to that negative 2, I keep wanting to put addition there. Don't know why. Negative 2 minus 3i Okay, when I add those together, you're going to see that I'm going to get 0 plus 0i. So those two are the additive inverses of each other. Now let's take a look at something a little bit more complicated. We're going to take a look at multiplication. Okay, and specifically we're going to take a look at the multiplicative identity. Okay, the multiplicative identity. And in this case here, the thing that we're looking for here, the multiplicative identity is going to look like this. It's going to be 1 comma 0. Okay, if you want to give it that kind of that original form there. If z is equal to 1 times 1 comma 0, then when you multiply this by some other number, okay, for example, if I multiply this z by some z1, I'm going to get z. Okay, and I'll show that to you right now here. Let's take that number 1 plus 0i. Okay, so 1 plus 0i. If I multiply that by some other value, x plus yi, okay, now there is that pattern that I've established before, but you could also just use distribution here. 1 times x is going to be x, 1 times yi is going to be yi. But 0 times x is 0, 0 times y is 0. So that portion right there kind of kills what would normally be the last two terms that I would get in terms of the distribution. And so we're just left with x plus yi. So there's how that works. Okay? Now, let's take a quick look. Well, one of the things that we can do here is prove the uniqueness of these particular values here, okay, of the additive and multiplicative identities just before we move on to the division there, the inverses, because multiplicative inverse is a little bit more complicated. Let's just talk about uniqueness here. Okay, so let's just say that we want to show, for example, I'll just start off with this. We'll make this quite simple here. We want to start off with showing that what I just created, let's say for the additive identity, is unique. Okay, so let's say I've got this z, and it's going to be x plus yi. And let's say I've got this other one here. Let's just say w is going to be u plus vi. Let's talk about the additive identity here. If I add these two together here, okay, let's say that I add the w here. I'm going to pretend that this w here is another additive identity. So I'm going to suggest here that z plus w is supposed to be z again. Okay, this is because it's the additive identity. We want to show that the 0, 0 is unique. So this means that x plus yi plus u plus vi must equal x plus yi. Now, if that's the case, that means x plus u must equal x. And if we look at the imaginary parts and add those together, y plus v must equal y. Now, bear in mind that these are just real numbers, that I'm combining them together with a couple other little rules there to create these complex numbers. X plus ux means u's got to be equal to 0. Y plus vy means v has got to be 0. So that is the only identity that works. Whenever I have this kind of scenario put together there, that means therefore 0, 0 is the only, okay, it's unique, is the only additive identity. Okay, and we can do a similar sort of thing to prove the uniqueness of the multiplicative identity. Okay, but just for the interest of time here, just that gives you a sense of how that works. Okay, so now we're going to take a look at the multiplicative inverse, and I've kind of left this off to the end here because it's a little bit more difficult. Okay, so we've talked about the commutative law, the distributive law, the associative law. We've talked about addition, additive identity, additive inverse. We've talked about the multiplicative identity. Now we're going to talk about the multiplicative inverse. And again, I've left this to the end here, a little bit more complicated. Let's first of all identify two complex numbers here. Let's say z is equal to x plus yi, and w is equal to u plus vi. Okay. Now, let's say that z multiplied by w is going to equal 1. Okay, or the multiplicative identity, if you will. Then what we know is if this is true, okay, then when you multiply those together, what we're getting here is xu minus yv plus I, okay, multiplied by yu plus xv. That has to equal 1 plus I0. Okay? Because that's what the multiplicative identity is, this 1 plus I0. Now what that means is xu minus yv is equal to 1. Yu plus xv has to equal 0. Now this gets us this system of equations. Now I'm not going to go through the process of solving this right now, simply because it's going to be a bit of a time crunch. This is already going a little bit longer. So what I'll do is I'm just going to give you what the answers are. And we're going to solve this in terms of the variable here, w. So u, solving this resulting system of equations, u is going to be x plus x squared plus y squared. And v is going to end up being negative y over x squared plus y squared. Okay, so this is the result, and this is what gives us this multiplicative inverse. Now it's important that this multiplicative inverse exists. Okay, there's some little rules that are going to pop out of that. You're going to recognize right away, like, yeah, that's an important policy, property here. So we do have this multiplicative inverse. We know the structure of it. Okay, and a couple things about that. And maybe I'll write it like this. So I know now that if I want z to the negative 1, or the inverse of z, multiplicative inverse of z, that's going to look like this: x comma x squared plus y squared, comma negative y over x squared plus y squared. And what this allows us to show everybody here is that, well, one of the things that this allows us to show here is going to be division. I'm going to show you how you do division here in just a moment. And I'll even give you a way of approaching this. It doesn't necessarily require you to think of it like this, but anyway, that does allow us to do division here. But it also shows that if you've got two numbers multiplied together and the result is 0, one of those numbers has to be 0. And I'll show you how this works here, so just note. And again, this is a really important result here. Note, if you've got two numbers multiplied together, or maybe let's do it like this. I want to show that if you've got z1 multiplied by z2 equaling 0, okay, that this implies that either z1 or z2 is 0. Okay, that's my goal here. So let me just start off with it. Let me show you here that if it works like this, that z2 has to be 0. Let's just take a look at z2. Okay, now z2 is going to be equal to, and I'm going to really take this slow, 1 multiplied by z2. Now I know that's obvious, but just bear with me. 1 I can create by multiplying, okay, the inverse of z1 by itself. Okay, so I can multiply those together. That's going to get me a 1 there. Now that's going to replace that 1 here. Now, because we've already established that the associative law is true, I can make this the inverse of z1 multiplied by those two together, right? Now, if that product is equal to 0, everybody, then I'm going to get z1 inverse multiplied by 0, and that's going to get me 0 at the very end there, okay? Now, that means, in this particular case here, you should notice here, that means if I work this all the way back here, if assuming that product is 0, we've been able to show that z2. That demonstrates to me that z2 was equal to 0 if that product there is 0. And you can show the exact same thing with z1 there. Now, that's one important aspect of this the presence of the multiplicative inverse. Here's another one that we can say this then. If you've got z1 divided by z2, that's the same as z1 multiplied by the inverse of z2. Okay? And that's kind of how we end up doing division. Okay, is instead of doing the division like you would normally think to do it, what we do here is we change it into multiplication of the inverse, the multiplicative inverse. Okay, when you think about that should ring a bell. You think about how fractions work. You know, when you're dividing fractions, you don't do division. You convert it into multiplication of the reciprocal, which in that particular case there is the multiplicative inverse. Okay, you multiply by the reciprocal. Here we're multiplying specifically by the inverse here. Now let me show you how that works. Okay, so if you've got Z1 divided by Z2, okay, now this is going to get a little bulky here, but the result is going to look like this. It's going to be x1 x2 plus y1 y2 over x2 squared plus y2 squared plus I, now this is the imaginary part, this is going to be y1 x2, okay, minus x1 y2 all over x2 squared plus y2 squared. Okay, so there is how division works. But let me show you how you can make this work out a little bit nicer here. Let me do an example here. Okay, but you should notice here at this point here that this little procedure here should point out that if Z2 is equal to 0, okay, and bear in mind what that means. That means your x and your y are both 0. This is undefined. Okay, so if both the imaginary and the real parts of a complex number are 0, if you've got 0 comma, well basically if x squared, x2 is 0, squared is 0, y2 is 0, squared is 0, division by 0 is undefined, so I can't let that happen. Okay. Now, there is another way that we can do this kind of division here. Let's just say, for example, let's take 1 plus 2i, and we'll divide that by 2 plus 3i. Okay. Now, I can do the division like they've set it up here, and in fact maybe I will, and I'll show you how you can approach this another way here. So I've got x1 x2, so it's going to be 2 plus y1 y2, so 2 times 3 is going to be 6, and this is going to be over what we've got here. We've got 2 squared, so 4 plus 2, so it's going to be 13, and this will be plus I. And then this is going to be y1 x2, so I got to go kind of across like this. This is going to be 4 minus x1 y2, so 3 over and again 13. Putting that all together, we are going to get 8 over 13 plus I over 13. Okay, so there we've done the division. I'm going to show you another way that you can handle that. Let's go back and do this again. What I'm going to do here is, and you will have seen something similar to this in one of your past math classes, I'm going to multiply numerator and denominator by the conjugate of the denominator. Now watch what happens. So the conjugate is going to be 2 minus 3i. This is something we're going to talk about a little bit later, a little bit more detail here. But watch what happens. So, and now I'm just going to distribute this out here. So I'm going to get 1 times 2 is going to be 2 minus 3i plus 4i. Now, watch this multiplication here. This is going to be 2i times negative 3i. What's going to be negative 6i squared, but the I squared is going to give you a negative 1, so it's going to be positive 6 all over. Now down here I'm going to get 4. Now this is a difference of squares here, but interesting thing, when you multiply difference of squares and you're working with just real numbers, you get this subtraction in between. But because my second term has got this I squared in it, that's going to produce another negative, so this is actually going to become plus 9. Now grouping together the real and imaginary parts here, so 2 plus 6 is going to be 8. This is going to be plus I over 13, which is exactly what we got up here. So there's just another way of handling that division. It's kind of cool. Okay, some other little things that you should be aware of, and I've got a resource here that some resources that I'm bouncing back around here. So I'm going to show you some identities. Yeah, and I'm pulling these some of this information from a book called Complex Variables and Applications. This is the 5th edition by guys named Churchill and Brown. And they are smart to point out some identities here. So first of all, Z1 divided by Z2 is the same as Z1 multiplied by 1 over Z2. Okay, which for some of you guys will be like, well, yeah, but not everybody is absolutely clear on that. So that is significant. Additionally, if I've got Z1, Z2, remember that because of the commutative law, if I multiply that by Z1 inverse, Z2 inverse, okay, because I can change the order of multiplication here, I can group together those things and I will get 1 times 1 when I multiply those together. As another thing that you should be aware of here, that if you've got Z1 plus Z2 and I've got that divided by a third complex number, I can in fact split that up just like you would have done with real numbers, okay? And I can do the same thing with the commutative law, or sorry, with grouping with division here. Okay, now let's take a look at some examples of how some of the arithmetic here works. So for example, let's say that I had the square root of 2 minus I, and I subtracted from that I multiplied by 1 minus the square root of 2 multiplied by I. So I got a lot going on here. First of all, what I would do, just like I would normally, I'd deal with the multiplication first. So I've got this I multiplied by this complex number. So up front here, I'm going to get the square root of 2 minus I. Nothing happened there. And then this is going to become, when I multiply that through, maybe what I'll do is I'll put a plus sign here. This will become negative I, because negative I multiplied by 1 would be negative I. And then watch this. The negative multiplied by the negative here would become a positive, true. So I would get positive root 2, but then the I multiplied by the I is going to give me a negative. And so you've got to constantly be thinking about that as you go through this. Now, I'm just adding two complex numbers together. So the real parts, when I add them together, the root 2 and the negative root 2 added together, it's just going to get me 0. And then negative I plus negative I is negative 2I. And that would be our answer. Okay? Let's try another one here. Let's try, let's say that we've got the number 2 plus 3I, and let's multiply that by, let's say, negative 2 plus I. Now, I can follow the rule that I've set up before about multiplying together complex numbers. Okay, that kind of summary rule. Or just think about it in terms of distribution. And remember that I times I is negative 1. So, I prefer to do it that way. 2 times negative 2, negative 4. 2 times I is going to be 2I. In many ways, we treat I as just like a variable. 3I multiplied by negative 2 is negative 6I. And then 3I multiplied by I is going to be 3I squared. But I replace I squared with negative 1. And so combining now the real portion of this, so it would be negative 7I. And then negative 7, I don't know why I said I there. And then 2I minus 6I will be negative 4I. Okay? Does that make sense? I hope so. Let's try another one. Let's see here. What happens? Let's try a division here, and well, let's make this a little bit more complicated. Let's try 1 plus 2I over 3 minus 4I. And let's add a couple here. 2 minus I over 5I. Okay. Now let's take a look at. I tell you what. Let's do the division first for both of these. Now, what I'm going to do here, and what I've set up before here, is I did give you a pattern that you can follow, but I'm going to multiply by the conjugate of the denominator, because I like that because it's using a tool that you have come across before in the past. So there's nothing different there. So when I see this 3 minus 4i, maybe I should zoom in a little bit on that. Okay, it's using a tool that you've seen before here. So I'm going to add to that 2 minus I. I've got 5i down here. Now I'm going to multiply this by negative 5i. And I'll do that into the numerator as well. Again, the binomial conjugate. This is like 0 plus 5i, so I'm going to multiply by 0 minus 5i. Now, let's deal with the denominator first because that's where the interesting things are happening here. So again, a difference of squares, but because of the I there, I end up getting 9 plus 16. Okay? Up in the numerator, I'm going to get 1 times 3 is 3, 1 times 4i is 4i. 2i times 3 is going to be 6i, 2i times 4i is going to be negative 8. 8 because of the 2 and the 4, negative because of the I squared. Over here, I'm going to add, I'm going to multiply, down in the denominator, I should deal with that first. 5 times negative 5 is negative 25 times I squared is going to be positive 25. And then I'm going to get 2 times negative 5i is going to be negative 10i. And then this would be negative 5i squared, so positive 5. Okay? Now, look, the denominator, this is a beautiful question because the denominators are the same. They're both 25. And so I'm going to now just add the numerators together. So my real terms here will be 3 minus 8 is going to be negative 5 plus 5 is 0, which is kind of cool. 4i plus 6i is 10i minus 10i is going to be 0. So the answer to this question here is when all's said and done, that's just going to be 0. Kind of fun. Let's try another one here. Number 4. Let's see what happens. Let's say I've got 5 and I divide this by 1 minus I times 2 minus I times 3 minus I. Let's see what happens when I do that. So I've got some multiplication down here in the denominator and then some overall division right here. So what I would do here, I'm going to ignore the numerator for now. I would just multiply 2 of these together right now. So let's just deal with that. 1 times 2, and I'm going to be kind of lazy here. 1 times 2 is going to be 2. And I'm going to put together the real terms because I know negative I times negative I would be positive 1 I squared. But that's going to make that negative 1. So I'm going to get 2 minus 1 is going to be 1. There's my real part. Now my imaginary part, okay, that was going to be negative 2i and negative I, so negative 3i. And then 3 minus I is that second term. Now let's multiply those together. 1 times 3 is 3, okay. Negative 3i times negative I, okay, the negatives are going to cancel, so I'm going to get positive 3i squared, but that's going to be negative 3. So I'm going to get positive 3 minus 3 is going to be 0. Okay, so the real part goes away. So what have I got for the imaginary part? Well, for the imaginary part, we're going to get negative I and negative 9i. So it's going to be negative 10i. All right, so that is going to reduce down. I mean, there's that 5 over 10. So this is going to be negative 1 over 2i. And then, because we typically want to pull that imaginary part up, I'm going to multiply numerator and denominator by I. I'm going to get an I squared in the denominator, which will be negative 1, which will cancel, and so I'm simply going to get I over 2 as my final answer. Perfect. Let's keep going. Let's try. This is kind of fun. So 5. Let's see what happens if I've got 1 minus I to the 4th. Now I'm going to start by making this 1 minus I squared squared. Okay? Whoops. Now 1 minus I squared. So it's 1 minus I times 1 minus I. So let's take a look at the real part first here. It's going to be 1 times 1. So 1. Negative I times negative I would be positive I squared, which is simply going to be negative 1. So when I put those real parts together, I'm just going to get 0 there. That's kind of weird there. Let's take a look at the imaginary parts. I'm going to get negative I and negative I. Okay, well that's easy. It's going to be negative 2I. Now this actually reduces down. That made this quite nice because what's going to happen here is that the negative 2 squared is going to become positive 4I squared. And then the I squared is going to make that negative. So it's going to be negative 4 when we put that all together. That's just really cool. All right, let's try maybe a different style of question here. Okay, question 6. Let's do this. Let's take a quick look here. Let's solve. Okay, let's solve z squared plus z plus 1 is equal to 0. You got to be able to see that there. Z squared plus z plus 1 is equal to 0. Okay. Now, there are a couple of ways that we could go about doing this. But to start off with, let's kind of be consistent with what we set up here. What I've got here, I know that z is going to be x plus iy squared plus x plus iy plus 1 is equal to 0. Maybe I should zoom out a little bit. This right here is going to look like this. This is going to become x squared minus y squared plus I times 2xy. I know that. Plus x plus iy plus 1 is equal to 0. Okay, so putting together the real parts of this, I'm going to get x squared minus y squared plus x plus 1. And then the imaginary parts are going to be here 2xy plus y is equal to 0. Okay, let's see what we get here. Okay, let's take a quick look. So now what I've got here, I got a couple of equations here. We've got x squared plus x plus 1 minus y squared equals 0. And then over here I've got this 2xy plus y is equal to 0. Now we're going to have to solve these two equations here simultaneously. Let's take a quick look at this one over here. This one looks a little easier. It's going to be y multiplied by 2x plus 1. Okay, so what happens here is either y is equal to 0 or x is going to equal negative 1/2. Okay? Now, if that's the case coming from here, let's take a quick look here. If we let y equals 0 over here, okay, if we let y equal 0, we're going to get, what are we going to get here? So actually, let's do case 1 here, where y is equal to 0. That means x squared plus x plus 1 is equal to 0. And that means x is going to have to be, I'm going to use the quadratic formula, negative 1 plus or minus the square root of 1 squared minus 4 times 1 all over 2 times 1. Now, I can see right away we're going to run into a problem. Okay, if I let y equal to 0, then look what happens here. I'm going to get the square root of a negative here. Now, you might think in this circumstance, well, that's really not all that much of a problem. I mean, we're talking about complex numbers. Yeah, and I get that. However, bear in mind what I did to solve this equation. I split this up into complex numbers, real portion, imaginary portion, and I know, okay, that when I equate these together, that these should behave the way real numbers behave. So right now, I'm not getting a real solution for x. Okay, there's no real number here. There's no real solution. So letting y go to 0 didn't work. So maybe what I got to do now is my second, and I'm running out of room here. My second scenario here was to let x equal negative 1/2. Now, if I do that in this equation, I'm going to get 1/4 plus 1/2 plus 1 minus y squared is equal to 0. Okay, so what have I got here? If I bring that y squared over, y squared is going to equal, okay, what do we got? We got 1/4 plus 1/2 plus 1 is going to be, actually, I was going to do that slightly differently here. Now I'm beginning to look at that y squared and think, I should approach that a little differently. 1 plus a half is going to be 3 halves, which is going to be actually probably easier to just do this in terms of quarters. I don't know why I'm fighting with that. So that would be a quarter plus a half is going to be 3 quarters plus a 1 is going to be 7 quarters. That doesn't look like the answer that I'm supposed to be getting for this particular problem here. Oh, I'm sorry, because x was negative a half. I'm sorry, that's why that... I was looking at this thinking, man, that's not working out to be the right number here, but that's supposed to be negative 1/2. Okay, well that makes more sense here, because what's going to happen here is this negative a half and the 1 will be a positive a half plus 4 will end up giving you 3 quarters. So this will be 3 over 4, which means y is therefore going to equal positive or negative root 3 over 2. And so my final solution, therefore, the complex solution of this will be negative 1/2, okay, plus or minus root 3 over 2i. Those are the answers that we're looking for. Anyway, there's a lot of other questions we could do. I hope that at least gives you kind of a flavor as to how we do some arithmetic and some solving with complex numbers.